So here is the question that I posed at the end of the first part of this lecture. And if you're doing this through Moodle, then in Moodle I gave you that it's symmetric under any rotations about the x-axis. And once you see that it's symmetric under any rotations about the x-axis, you don't have to worry about the 180-degree rotations because they're already included in that. So I gave you that in Moodle, and it was up to you to figure out which of these other ones were symmetries of it. And hopefully you can see that if you reflect it through any plane perpendicular to the rod, or any plane that passes through the middle of the rod, then the rod will be unchanged. And you can also translate it along the x-axis. It's actually just like the example of translational symmetry that I gave when I was introducing the idea. And you can rotate it by 180 degrees about the y-axis or the z-axis. However, if you rotate it by any other angle about the y-axis or the z-axis, it doesn't look the same anymore. And so it isn't symmetric under those. And similarly, if you translate it along the y-axis or the z-axis, you'll see that change. And so it isn't symmetric under those transformations. You might be wondering what all of this discussion of symmetry has to do with what we've been studying. Well, here it is. If you think about the symmetries of a charge distribution, any geometric operation on a charge distribution which leaves the distribution unchanged must also leave the electric field unchanged. After all, if you don't move the charges, the field that they produce won't change. On the other hand, any geometric operation that does change the configuration of the charges must also change the field, just like moving the charges would change the field. Well, this tells us that whatever the symmetries are of the charge distribution, the field that that charge distribution produces must have exactly the same symmetry. This is going to be very useful along with Gauss's law as a way of easily calculating fields due to highly symmetric charge distributions. I'm not going to show you yet how you use it with Gauss's law, but I will demonstrate the idea of the symmetries of the charge distributions and fields matching using a dipole. So think about this dipole and realize that while the field that I've drawn for it is in 2 dimensions, it's really a 3-dimensional field. So if you think of an axis that passes through both of the charges, clearly rotating about that axis doesn't move the charges, and similarly, it will not change the field. Similarly, a reflection through any mirror plane that passes through both of the charges won't change the field either, and it doesn't change where the charges are. On the other hand, if you reflect through this mirror plane, which is halfway between the charges and perpendicular to the line through them, that will exchange the positions of the charges, and as a result, all of the field vectors flip right to left. And so reflecting through this is not a symmetry of the charge distribution, and similarly, it's not a symmetry of the field. So this is just an example of how the symmetries of the charge distribution and the symmetries of the field must always match. You already know that the symmetries of an infinite line and an infinite cylinder is just what you might think of as a thick infinite line, and so it has all the same symmetries. So let's use the symmetries of the infinite cylinder to draw conclusions about the electric field that it produces. I'm going to start by thinking about the end view, and I've drawn myself several copies so that I can try out several different things. So first of all, we know that it's symmetric under any reflection through a plane that passes through its center, and so that allows us to eliminate several possibilities. For example, if the field had any components pointing around the rod, like so, that violates this symmetry because, for example, this becomes that, and this becomes that, and these exchange like that. Similarly, if the field is somewhat, I will say, offset from the center. Something like, say, this. That also violates this symmetry because, again, this moves over to here, and this moves over to here, and this flips direction and ends up over here, and this flips direction and ends up over here. Another one that is impossible is a field where, say, the field is stronger in the vertical direction than it is in the horizontal direction at the same distance out. Now, this does not violate this symmetry. This is symmetric under reflection through this line. However, what it violates is symmetry under rotations about this axis, because if this vector rotates down to here and this vector rotates down to here and so on, that will have changed the field. So you can try various other possibilities, but the only possibility in this end view is if the field is pointing radially out everywhere, and at any particular distance out from the cylinder, it has to have the same strength everywhere at that distance. Now, the symmetry doesn't tell us whether it stays the same or gets weaker or stronger as we move out from the cylinder. However, we know that electric fields tend to get weaker as we move away from the source, and so we could certainly guess that they will get weaker as we move out. Now I'll think about the side view. So first of all, let's think about the E-field vectors in the plane of the page, and suppose they were tipped in some direction, say like this. Where I am not drawing perspective, I'm suggesting an E-field where the vectors that are in the plane of the page are pointing at some angle from vertical. Well, that's impossible because this cylinder has symmetry under reflection through any plane perpendicular to it, and if we carry out that reflection on these vectors, then they change which direction they're tipped in, and so that cannot be a correct field. That tells us they're not tipped. It tells us that they all have to point, just like we know that they point radially out when we're looking end on. It also tells us that they point in a side view perpendicular. Now, suppose their strength varied with position along the length of the cylinder in some way, and I'm just making up some way. Doesn't matter what way. Remember that the cylinder has translational symmetry along its long axis. However, if we shift this by any arbitrary amount along the length of the cylinder, that's a different field. And so this field doesn't have the translational symmetry that the cylinder does. And so that tells us that the magnitude has to be the same at every point along the cylinder. Now, the fact that the field has to be symmetric under reflections through any plane that passes through the middle of the cylinder tells us that whatever the field is at some distance above the cylinder, it has to have the same magnitude below, but point in the opposite direction. Finally, let's see a symmetry that the system doesn't have, and what that tells us about the field. We know that the cylinder is not symmetric under translations perpendicular to its length, and so we don't expect the field to be symmetric under that. What that tells us is that as we go farther away from the cylinder, say in the upward direction on the page here, we expect the field will probably change. Again, symmetry doesn't tell us whether it will decrease or increase, but our intuition that we know fields tend to get weaker from their sources tells us that the nature of the change is almost certainly that the field must get weaker as we move farther away from the cylinder in this direction. I'm going to contrast the infinite line with the finite line. So note that it will have all the same symmetries as the infinite line, except for a few. So note, it'll have the symmetries about planes that pass through the line through it, and rotation about the line through it, and the 180-degree rotations about axes perpendicular to that. However, it is not an infinite object, and so it can't have any translational symmetry, and so it loses that symmetry under translations along the x-axis. Second of all, the less obvious difference is that the infinite line was symmetric under reflections through any plane perpendicular to the line, no matter where that plane was. But for the finite line, the only one of those planes it's symmetric under is the reflection plane right through its center, or in my choice of axes where the origin is at the middle of the line, the yz plane itself. Because the finite line of charge is less symmetric than the infinite line of charge, symmetry tells us less about its field. However, note that symmetry is still very useful. If you think back to the electric fields unit, we concluded for a finite line of charge that out along the y-axis here, the E field would have to be perpendicular to the line of charge. Similarly, you can conclude that this proposed field here is wrong. It can't possibly be right, because the rod is symmetric under reflection through the yz plane, but this field isn't, and so we can reject that as a possibility. And we can reject many other possibilities. However, unlike the infinite line of charge, where symmetry tells us more or less exactly what the shape of the field is, symmetry isn't enough to tell us everything about the shape of the field for the finite line. All of these proposed fields have the right symmetries to be possible fields for the line of charge, and symmetry can't tell us anything more. If you think about superposition of fields, you'll probably see that the real field due to the line must be something like this, but it wasn't symmetry that told you that. I'll just finish up by summarizing some important symmetries that we're going to see as we go along. So we've already looked at the infinite line of charge, and note that what I'm really drawing is a cylinder of charge. A line is just the special case of a cylinder that has zero radius. So this is what we refer to as cylindrical symmetry. Another one that we'll see is an infinite plane of charge, which we met during the electric fields unit. And so planar symmetry is going to be an important one to us. And finally, the granddaddy of all symmetries, the most symmetric object of all, is a sphere. Spherical symmetry is absolutely the most symmetry any object can have.